The density of prime numbers near a large integer x is precisely 1 divided by the natural logarithm of x. This foundational result, the prime number theorem, quantifies the asymptotic distribution of primes. It states that the prime counting function, pi of x, is asymptotically equivalent to x divided by the natural logarithm of x. While this gives the average density, it reveals nothing about the fine-grained fluctuations in prime distribution. Understanding these fluctuations requires moving beyond real analysis into the complex plane, specifically through the analytic continuation of the Dirichlet series defining the Riemann zeta function. This function, initially defined only for complex numbers with real part greater than 1, holds the key to the precise location of every prime number. The Riemann zeta function, denoted zeta of s, is initially defined as the infinite sum of 1 divided by n raised to the power of s, where n ranges over all positive integers. This series converges absolutely only when the real part of the complex variable s is strictly greater than 1. Bernhard Riemann extended this definition using analytic continuation, transforming the function into a merillomorphic function valid across the entire complex plane, except for a simple pole at s equals 1. This continuation allows us to study the function's behavior in the critical region, where the prime distribution secrets are hidden. The functional equation relates zeta of s to zeta of 1 minus s via the gamma function and trigonometric terms, establishing a symmetry around the critical line.
The complex plane is divided into 3 regions by the zeta function's behavior. The region where the real part of s is greater than 1 contains no zeros. The region where the real part of s is less than 0 contains the trivial zeros, located at the negative even integers, -2, -4, -6, and so on. These zeros are easily understood and arise directly from the gamma function term in the functional equation. The remaining area, the critical strip, is defined by complex numbers s, where the real part is strictly between 0 and 1. This strip is where the non-trivial zeros reside, and their precise locations dictate the accuracy of prime number approximations. The Riemann hypothesis asserts that all non-trivial zeros of the Riemann zeta function lie exactly on the critical line. This critical line is defined by the equation where the real part of s equals 1/2. If the hypothesis is true, the zeros are perfectly aligned, implying a highly regular, though oscillatory, distribution of prime numbers. If a single non-trivial zero were found off this line, the hypothesis would be false, suggesting a much more erratic and unpredictable distribution of primes than currently assumed. Proving this hypothesis is one of the 7 Millennium Prize problems, carrying a $1 million reward. The distribution of primes is quantified by the prime counting function pi of x. Riemann introduced a refined counting function r of x, which is a smoother approximation than x divided by the natural logarithm of x. The error term between the actual count pi of x and the approximation r of x is directly controlled by the location of the zeta function's non-trivial zeros. Specifically, each zero contributes an oscillatory term to the error. The closer the zeros are to the critical line, the smaller the magnitude of these oscillations, leading to a tighter fit between the approximation and the actual prime count.
Riemann's explicit formula provides the direct mathematical link between the non-trivial zeros and the distribution of primes. This formula expresses the weighted prime counting function, psi of x, as a sum involving the main term x, a term related to the pole at s equals 1, and a sum over all non-trivial zeros, rho. Each term in the sum over zeros is proportional to x raised to the power of rho divided by rho. Since the real part of rho determines the growth rate of this term, the Riemann hypothesis, stating that the real part of rho is always 1/2, guarantees the slowest possible growth for the error terms. If the Riemann hypothesis holds, the error term in the prime counting approximation is bounded by a constant times the square root of x multiplied by the natural logarithm of x. This bound is significantly stronger than any known unconditional bound. The oscillatory nature of the error term is caused by the imaginary parts of the zeros. These imaginary parts act like frequencies, creating a harmonic analysis of the prime numbers. The hypothesis ensures that these oscillations are damped as quickly as mathematically possible, confirming that primes are distributed as regularly as random numbers, despite their deterministic nature. Extensive computational efforts have verified the Riemann hypothesis for the first 12 trillion non-trivial zeros. These calculations, performed using algorithms like the Odlisker-Schoenhage algorithm, provide strong numerical evidence but do not constitute a proof. The zeros appear to follow the statistics of eigenvalues of random Hermitian matrices, a connection formalized by the Montgomery-Odlisko law. This unexpected link to random matrix theory suggests a deep underlying structure, potentially related to quantum chaos, further fueling the belief in the hypothese's truth.
The truth of the Riemann hypothesis immediately implies the correctness of numerous theorems currently proven only conditionally. For instance, it guarantees the tightest possible bounds for the gap between consecutive prime numbers. In computational number theory, the hypothesis justifies the efficiency of several algorithms, including those used in primality testing and factorization. While not directly used in current cryptographic standards like RSA, which rely on the difficulty of factorization, the hypothesis provides the theoretical bedrock for understanding the complexity landscape of integer arithmetic, impacting future security protocols.